Welcome back to a new Marcus Maths video. Today we're going to be going over the Unit 1 Limits and Continuity module exam for AP Calculus BC. Sorry for the last couple days with a lack of uploads. I unfortunately had an illness that I am still recovering from now. And, well, I'm just glad to be back. We're going to be speed running these 30 problems right here. So, I'm going to be explaining each as I go through. Make sure to subscribe and like the video if you haven't already. We're going to be continuing with this practice, both AP Calculus and SAT Math and Reading on the weekends. But let's go ahead and get started immediately. We're going to find the x values at which h has a jump discontinuity. So the function h, we have the graph right here. All we need to know is that a jump discontinuity is when the function has a gap or it jumps between y values. We can actually see that happen twice. At the x value of 1, the function is going to jump from the value of 2 to the value of 3. And then very similar at the x value of 2. So at the x value of 1, we had a jump. At the x value of 2, we have another jump from the x value of 6 to the x value of negative 7. So that means we're going to have two jump discontinuities at the x values of 1 and positive 2. So B and C, the other answer choice, x equals negative 3, that is only a whole discontinuity. As you can see, there is just an undefined value in the midst of a function. In the midst of the function values. So let's go ahead and move to our next question. Can we use the intermediate value theorem? If you remember the video where we went over each of these individual skills, yeah, if you have any problems with these, just ask me in the comments and I'll direct you to the exact video, quiz 1, 2, 3, 4, 5, 6, that goes over that exact topic where I go a lot into depth a lot more. So this question asks if we can use the intermediate value theorem to say the equation h of x is equal to 4 has a solution between 3 x and 5. Well, we need to determine is the function continuous on the interval and if the value 4 is in between h of 3 and h of 5. So first of all, we have an exponential function right here. If you know the basic shape of these curves, they are defined at all values and they're continuous at all values. There are no discontinuities in an exponential function. So answer choice A is not going to mean we can't use the intermediate value theorem. Now let's test. We're going to substitute in 3 and 5 into our function and see if 4 is in between those two values. 2 to the power of 3, we know that's 8. 2 to the power of 5 is equal to 32. 4 is not in between these two values. So B is a correct justification saying that we cannot use the intermediate value theorem to justify that h of x is equal to 4. We could say that h of x is equal to 10 since 10 is in between 8 and 32. However, since 4 isn't, we cannot use the intermediate value theorem here. Okay, find the limits of f at negative and positive infinity. We're just going to look at the horizontal asymptotes. So as we approach negative infinity, we can see that we're going to approach the y value of 0. So as the limit of f of x as x approaches negative infinity is 0. We asymptote towards 0. And now approaching positive infinity, we're going to the right. And we can see that we're approaching negative 4 here. So the limit of f of x as x approaches infinity is simply equal to negative 4. We have our two limits. On to our next one, we have a table and we're trying to approximate the limit of h of x as x approaches negative 8. Now, the general rule of thumb is that we want increasingly closer increments that get very close to our value of negative 8, and we want to have that from both the left and the right side. So we want to be approaching negative 8 from the left, meaning values like negative 8.05, etc., getting smaller and smaller, and then from the right would be negative 7.9 in a way. And as we can see, A only approaches from one side, B does not use small enough increments in the x values, of course, but C has both of the constraints. We're going increasingly small increments from the left and the right, and we can see that we approach that value of positive 5, so there is a set conclusion. Okay, the function g is defined over all real numbers. This gives selected values. We're trying to look the limit as g of x as x approaches 0 from the right. From the right, we're only going to be looking at these values here that are to the right of 0. And as you can see, as we get closer and closer, each step gets closer to 0. Our y value gets closer and closer to positive infinity. It looks like it's unbounded. It's increasing at an increasing rate. which means the reasonable estimate is going to be unbounded. It's going to go off into infinity. Okay, another question here. Let g of x equal 2 over x minus 3 squared. Select the correct description of the one-sided limits of g at x equals 3. So how I would describe this, I would simply substitute in a value to the right of 3 and an x value to the left of 3, and then evaluate. Are we going to be increasing at an increasing rate or decreasing at a decreasing rate, or something else? Let's test that. Let's start with 4 and then to 3.5 to represent approaching from the right side. So when we have 4 minus 3 is 1, squared is 1, 2 over 1 is 2. So we get 2 as the y value, and then 3.5, we get 0.5 squared. 0.5 squared is 0.25, and 2 divided by 0.25 is 8. And you can see if you try 3.25, you're going to be increasing at an increasing rate. So that means as we approach 3 from the right, we're going to be approaching a positive infinity as our y value. We can get rid of c and d. Now approaching 3 from the left, we're going to use very similar things, but let's now use 2.5 and 2.75 to get a good illustration of what happens to our y value as our x value approaches. Now, if we wanted to actually get a complete approximation, we would want to do the very small increments that we saw in the previous question. So 2.5 minus 3 is negative 0.5. Negative 0.5 squared is positive 0.25 divided, and 2 divided by positive 0.25 is 8. 2.75 minus 3 is negative 0.25, but the square is going to cancel that out. A quarter of 0.25 is 0.0625, I believe. And 2 divided by that, I do not know of the value, but I think it's around 30 or 40. As we can see, we're increasing at an increasing rate. We're going to positive infinity. So answer choice A is correct. Notice that the squaring notion is the most important here, because if we're getting squared, it's getting rid of any negative element. So we're not going to be approaching negative infinity with these values. Okay. Dashed lines represent asymptotes. This is a function h, which limit expressions agree with the graph. Let's just break this down. A, B, and C individually. So as x approaches 4, we can see the limit approaches negative infinity. That is not the case. Our left side approaches positive. Our right side approaches negative infinity. So the limit does not exist or is unbounded. So A is not correct. B, as x approaches negative 2 from the left only. So we're going to look at the left part of the function. As h of x approaches negative 2, we can see that it approaches negative infinity. So that is indeed correct. And then if does the whole limit approach negative infinity? We take a look at the right side. It exhibits the same behavior. Both sides approach negative infinity. C is also a correct answer. Okay. What is a reasonable estimate for the limit of g of x as x approaches negative 5? Let's take a look at our one-sided limits. That's how we evaluate these. Our left side is unbounded to positive infinity. Our right side is unbounded to negative infinity. So the limit does not exist. Okay, next one, we have a jump discontinuity at x is 0. So we cannot find the limit here, because our left-sided limit is about 5. Our right-sided limit is about negative 5. When the one-sided limits are not equivalent to each other, the limit at that value does not exist. So D is, once again, the correct answer here. Okay, find the limit of the sine of 2 of x divided by the cosine of x. Now, with these more complex trigonometric limit expressions, we just need to understand the double angle identities from pre-calculus. Now, if you do not know what those are, highly recommend refreshing on all of our different trigonometric identities, including our double angle identities, ways to rewrite sine and cosine or the other trigonometric functions into each other, and also Pythagorean identities. Also, using difference of squares with trigonometric functions. These will all help us whenever we move to our future units as well, but they are definitely a key focus when we're dealing with these limits, because if we try to substitute x approaches pi over 2 into both numerator and denominator, we get cosine of pi over 2, which is equal to 0. So when the denominator is 0, numerator is 0, we're in indeterminate form. We need to eliminate something extraneous here. So in this case, we're going to be using the double angle identity of sine, and that is equal to, well, sine of 2 of x, double angle. We can rewrite that as 2 times the sine of x multiplied by the cosine of x. So that's our new numerator. These are equivalent to each other. Just highly recommend memorizing this kind of stuff. Alright, divided by the cosine of x. We can cancel out the two cosines of x. We're left with just 2 sine of x. We can directly substitute in pi over 2 here. Sine of pi over 2 is equal to 1. 2 times 1 is 2. So the answer for this one is answer choice C. Okay, we're going to be evaluating this limit as x approaches infinity. When x approaches infinity, we only need to pay attention to our leading values here. And since the highest degree term in the whole polynomial is x to the power of 3. When that is in the denominator, think if the denominator is equal to infinity, what's 1 divided by infinity going to be? It's going to be equal to 0. If you split 1 an infinite amount of times, it gets infinitely small, and you have equal to 0. So whenever our degree, when we're approaching infinity, is higher in our denominator, the limit is simply equal to 0. Okay, the limit of cosecant. Very important. We're just going to rewrite, well, as x approaches 0. Instead of evaluating the function as itself, we're just going to rewrite cosecant as 1 over sine of x. This is a trigonometric identity once again, and then we're just going to evaluate the limit as this function approaches 0. So we're just going to directly substitute. The sine of 0 is equal to 0. 1 divided by 0 is unbounded. The limit does not exist. Notice we just have sine of x, so we're not going to be able to use any other trigonometric identities to cancel this one out. It's just going to be unbounded whenever we have 0 in the denominator and a different number in the numerator. It's unbounded. When we have 0 in the numerator as well, it's indeterminate form. And that way we can do something to manipulate. Okay, we have a piecewise function here, 2 parts. We're going to find the limit of g of x as x approaches -1. We need to look at both sides here. Okay, we're going to directly substitute into the numerator. We get -1. Let's directly substitute into the denominator. We also get -1. When the left side and right sides are equal to each other, the limit, we can set the whole limit equal to -1 as well. Okay, we're going to be just evaluating this function right here. For the limit as x approaches -1. If we directly substitute, we will yield indeterminate form. So we're just going to factor this. First of all, we're going to factor out x squared from each term in the numerator, as it represents the greatest common factor. And then when we do that, we are left with the quadratic, x squared plus 2x plus 1. We cannot factor out any greatest common factor in our denominator, so we're simply going to factor this quadratic like normal. We're going to think what two numbers multiply to 1 and add to +2. Well, those are just 1 and 1. So we can rewrite the quadratic as simply x plus 1 squared, since we have this factor twice, divided by x plus 1. That means that we're going to cancel out one of them. So we are simply left with x squared times x plus 1 in the numerator. And when we do this, we can now directly substitute. We have nothing left in the denominator to make us equal to undefined. Okay, our left side is equal to +1, and our right side is equal to 0. +1 times 0 is simply equal to 0. So the limit is equal to 0. Okay, next question here. We cannot directly substitute. We're left with 0 in the denominator. But when we do that, notice we're not left with 0 in the numerator to yield indeterminate form. We're left with a number, meaning the limit is unbounded at this value, and it thus does not exist. Okay. Find the limit of x as we approach -infinity. This is quite important. Let's ignore this other term. It's not a high degree enough. Let's just take the square root of that first term here. We get 3x to the power 6. Now notice, if we substitute in -infinity, the even power is going to turn this into +infinity, both in our numerator and denominator. So we can simply get rid of the negative aspect. These two are going to cancel out. 9 divided by 3 is equal to 3. So the limit as we approach -infinity is equal to 3. Very important that if this was, let's say, both of these were 5s and we were approaching, well, let's say just one of these were 5. The numerator was 5 and the denominator was 4. We wouldn't even pay attention to the denominator, too low of a degree. But if our numerator was x to the power of 5, we would notice that to the power of 5, a negative value to the power of 5, it is simply negative yet again. So then that means our limit would be a negative value. Very important to understand what cancels out our negative value and what does not. On to our next question, number 17. We're over halfway there, so good job. If you're still watching the video, it's great to study. Okay, these are the graphs of the functions f and g. Dashed lines represent asymptotes, which functions are continuous, meaning that there's no breaks, there's no holes, there's no discontinuities, there are no unbounded parts to worry about. That is continuity. So from -3 to +1. So as we can see here, we had defined from -3 to +1. There are no breaks. So answer choice A works. We don't have to worry about this part over here since that's not part of -3. That's to the left. Okay, and then -3 to +1. We don't have that case for answer choice B. Notice we have a giant infinite discontinuity in the middle of that interval. Okay, answer choice A is the only correct one here. Moving on, what is the value of k? Notice if it's continuous, our right-sided limit has to be equal to our left-sided limit. So we're just going to find the left-sided limit. We're going to directly substitute here. Notice it has to be a value where this is undefined for 0. Okay, so we're just going to look what value is our function in the top. 3x over x e times e to the power of x. What is it approaching from the left and right side? Okay, we can just eliminate the discontinuity by dividing x and x. Then we have 3 over e to the power of x. We can directly substitute in 0. E to the power of 0 is 1, so it's approaching 3. But since our top piecewise is undefined at 3, so there would be a hole at x equals 0 at the y value of 3. So to fill this hole and make the h of x continuous over all real numbers, we're just simply going to add in a value of 3 at x equals 0. Okay, moving on to a new problem. We are dealing with limits with square root functions. How we eliminate the discontinuity here is that we're simply going to use conjugates. So how we use conjugates, we're just going to multiply both the numerator and denominator by the conjugate of whichever part of the fraction has the square root. So how this works, we have our function. We're just simply going to multiply both the numerator and denominator by, instead of 5 minus square root of 3x plus 28, we're going to do 5 plus square root of 3x plus 28. Now we're going to both numerator and denominator. So our function maintains equivalency. Plus 28. Okay, now we're going to multiply. We get 25 minus 3. Well, very important to keep this in parentheses. 3x plus 28. And then our denominator is simply going to be x plus 1. Times our conjugate that we multiplied. 5 plus square root of 3x plus 28. Okay, we're going to combine 25. Well, we're going to distribute first. Negative 3x, negative 28. 25 minus 28 is negative 3. So we have negative 3x minus 3. On the numerator, we can GCF negative 3 out. So we're left with negative 3, parentheses, x plus 1 on our numerator. Let me go ahead and replace our numerator with that value, because if you kind of notice, we are getting that same parentheses on both the numerator and denominator. This is a discontinuity that we are currently eliminating. Okay, so we're going to cancel that out, that x plus 1, and now we're left with negative 3 over 5 plus square root of 3x plus 28. We're simply just going to directly substitute in our value for the limit here into our function. So 3 times negative 1 is negative 3, plus 28 is 25. Square root of 25 is 5. 5 plus 5 is 10. We're left with negative 3 over 10, and that is our value. Yeah, so there's nothing wrong with the square root being in the denominator. It's simply we can use this conjugate to get to a point where we can eliminate a discontinuity. Okay, we have this function up here. We're going to use a flowchart to find the limit of f of x as x approaches 5. So we're just going to take this step by step and then use this flowchart to map our steps at the very end. Okay, first step is to directly substitute to see what we're dealing with. Into the numerator, we get 25 minus 25, which is 0. Into our denominator, we get 25 minus 50 plus 25, which is also 0. We're left with 0 over 0, which is indeterminate form. So we did direct substitution, and we're left with indeterminate form. From here, since we have quadratics, we're going to factor. Now, numerator is difference of squares. When we factor, we're left with x plus 5, parentheses x minus 5. Then our denominator is perfect square trinomial, so we are simply left with x minus 5 squared, meaning we have this factor twice. Okay, then we're going to cancel out one of the factors. Notice now we're left with x plus 5 on the numerator, and then x minus 5 on the denominator. And then we're going to directly substitute once again. 5 into the function, we're left with 10 over 0, which means we have an asymptote, as shown with b. Okay, so let's illustrate our steps. We directly substituted, and then we got indeterminate form. So then we factored, and then we directly substituted again, and then we were left with an asymptote. So this was our order, and it is the correct answer. Okay, we're going to evaluate this limit as x approaches 0. Let's take a look at our left and our right side. What value are we approaching? We can see that we're roughly approaching the same value of 2.9 on each side. Since the left and right sided limits are equal, we can say that we have a limit for the whole function. Okay, on to the next one. We're going to use the squeeze theorem. How the squeeze theorem works, we're going to, we cannot evaluate at the limit of x approaches 0. So we're simply going to find a function that is above f of x and very close to that value at the limit, and then one that is below f of x in the whole range and also very close to the limit, so we can squeeze the limit of f of x between those two functions, and then we can approximate the limit from that information. So we can see this is really well done. H of x is above f of x for all the values approaching x, approaching 0, and g of x is below, and they both have a limit of 1. So that means if one's above and one's below, and they both have a limit of 1, that squeezes f of x to also equal the limit of 1. So this suggestion, let me just double check. We're proving, yep, that the limit is equal to 1, and then we use these two functions, and it is done correctly. Okay. All right. We are going to be finding the limit as x approaches 0 as the two functions multiply with each other. So how we're going to do this, when we have two different functions and we have a jump discontinuity, what we're going to do is we're going to take the one-sided limits, multiply them with each other, and our left-sided limits, multiply them with each other, and our right-sided limits also multiply them with each other, and then see if we get equal left and right-sided limits. If we do, then the limit exists. If not, then it does not exist. So our left-sided limit for f of x is 1. Our left-sided limits of h is 3, so 1 times 3, we get 3. Then for f, the right-sided limit is 1, and the right-sided limit of h is 0. We get 0 for the right side of limits. Our left and right side of limits are unequal, so the limit does not exist, unfortunately. Okay, we're going to find the limit as x approaches 0 of negative 2 times g of x. We simply evaluate the limit of x approaches 0 of g of x, and then we multiply the answer by 2. You could rearrange this like this right here. Negative 2 times the limit as x approaches 0 of negative 2. No, not negative 2 anymore. We just moved that outside. Of g of x. Okay, the limit is, well, even though it's undefined, we can see from the left side it approaches 3, from the right side it approaches 3, so the value is equal to 3. We multiply 3 times negative 2, we're left with negative 6. Alright, we have another piecewise. We're going to see if we're continuous. So first we have to see, are we defined at 0? We are defined at the square root of pi when we substitute them in. So that's our first step for continuity. Our next step is, are the left-sided limit equal to the right-sided limit? Let's test that out. Okay, the sign of 0 is equal to 0, so our left-sided limit is 0. And then when we substitute in 0, we get the square root of pi. Since the square root of pi is unfortunately not equal to 0, our one-sided limits are not equal. Thus, we do not have continuity at x equals 0. So no is the correct answer here. Okay, moving on to question 26. Let g be a continuous function on a closed interval where g of negative 3 is 0 and g of 3 is 6. Which of the following is guaranteed? So, intermediate value theorem guarantees that there's a value in between 0 and 6 across the interval negative 3 and 3. So from 0 and 6, so the value has to be equal to 5. Negative 2 is not in between 0 and 6. And then we say between the x values of our interval, negative 3 and positive 3. So answer choice A is the only one that fulfills both those constraints. Don't let these types of questions confuse you. Okay, we have a composite function here. We're going to find the limit as x approaches 0 of f of x first. That is equal to negative 1. So now we're going to find the limit of g of x as x approaches negative 1. Limit of g of x as x approaches negative 1 is equal to positive 4. So that means the limit of the value of the composite limit is simply equal to positive 4. Okay, we're going to consider the graph of h, which limit expressions agree with the graph. Another one where you just go answer choice by answer choice by answer choice. Start with answer choice A. Limit of h of x as x approaches negative 3. That's this value right here, is equal to 3. No, it's equal to negative 3 on both our left and right side. Answer choice A is not correct. Limit of h of x as x approaches positive 3 from the right. We can see that's equal to 1. It's that right side of the graph right there, so B is indeed correct. And then from the left, it does not exist. From the left, we can see it's equal to negative 3. So answer choice C is unfortunately not correct. Answer choice B is the only correct answer here. Okay. Select all the correct statements about h at x equals negative 2. We can see we have an infinite discontinuity. Left side's going to positive infinity, right side's going to negative infinity. Okay, both of the limits exist. Well, they're going to infinity, so they do not exist. The limit does not exist. Are we defined? Nope. And are we continuous? Well, we have to be defined, and both limits equal each other. So they're definitely not continuity here. So none of the above is the correct answer. Okay, which of the following functions are continuous for all real numbers? Tangent and x to the power of 3. Well, cubic functions are are continuous if we just remember the basic shape of them like that. Tangent, unfortunately, is not, because remember, tangent is simply opposite over hypotenuse, or sine over cosine, and there are values where cosine is equal to 0, making the function not continuous at that point when the denominator is equal to 0, of course. So H is the only correct answer here. And that is 30 questions. That is our complete Unit 1 exam. The most difficult question I'd say here is definitely the double angle, just because you need to know that prior knowledge from pre-calculus in order to answer it. But if you have any additional questions about Unit 1 limits and continuity, please let me know in the comments. We're going to be looking over Unit 2, differentiation, starting tomorrow. So definitely look forward to those videos. I will see you then as we continue this AP Calculus study. Unit 1 out of 10 units done. Make sure to subscribe and like the video if you haven't already for lots of AP Calculus study coming. Goodbye.